Hey everyone. So today we're going to pull back the curtain on a piece of tech you use literally every single day, but probably have never even heard of. It's called sputtering, and it's the secret sauce behind the anti-glare on your glasses, the circuits in your phone, you name it. Let's dive in.
I mean, really think about that for a second. We're talking about coatings that are just a few atoms thick, but they have to be perfectly even and super durable. You can't just, paint them on with a tiny brush. The real answer is something way cooler. It's basically like spray painting at an atomic level. And there's the official definition, sputtering. So, in a nutshell, imagine you're in a vacuum chamber. You take a block of your source material, this is your paint, and you blast it with super energized particles. This literally knocks atoms off the block. And those atoms fly across the chamber and stick to your target, your canvas, creating this incredibly thin, perfect film. It's just mind-blowing precision. All right, to really get this, we're going to break it down into 4 key parts. First, we'll peek inside the sputtering chamber itself. Then we'll look at what's powering this whole process. After that, we'll talk about finding the perfect recipe. And finally, how do you even know if it worked? We'll check out the quality control toolkit. Okay, so before you can do any kind of atomic spray painting, you need the world's cleanest studio. And that's exactly what the sputtering chamber is all about.
Everything here is about absolute control. First, powerful pumps create an ultra-high vacuum, sucking out every last bit of air, dust, water, anything that could mess things up. Then, a very specific gas, usually something inert like argon, is piped in to create the perfect atmosphere for sputtering. And those multi-magnetron setups? Think of it like having multiple spray cans with different colors. It lets you create really complex, layered materials all in one go, with just incredible precision.
All right, you've got your pristine chamber. Now you need the muscle. You need the energy to actually blast those atoms off your source material. This is where the power supply comes in. And believe me, which one you pick makes all the difference. So the 2 big players are DC and RF. DC, or direct current, is like a steady, constant stream of energy. It works great for materials that conduct electricity, like metals. But what if your paint is a ceramic, which doesn't conduct electricity? Well, that's where RF, or radio frequency power, is a game changer. It uses a rapidly alternating field that gets the job done, no conductivity required.
Oh, but we're not done yet. Not by a long shot. For even finer control and seriously high-quality films, engineers have come up with even more advanced sources, like Pulse DC and this incredible technique called HIPIMS. This is where the real cutting-edge stuff starts to happen.
So you might be wondering, why bother with all these fancy systems? Well, because the results are just better. We're talking about films that are way denser, so they're tougher, they're more adherent, meaning they stick to the surface like you wouldn't believe. And the bottom line is, you get to be an architect for the material's internal structure, atom by atom. This is how you create those insane scratch-resistant coatings you see on high-end watches or surgical tools. So we've got the chamber, we've got the power, but that's just the hardware. Just like baking, having a great oven doesn't guarantee a great cake. You've got to have the right recipe. And honestly, I love this analogy of molecular baking. It's perfect because every single variable, the pressure in the chamber, the temperature, the power level, the gas flow, it's all an ingredient. If you change just one tiny thing, you can get a completely different result. And just look at how all these things play together. Take substrate temperature. Just by heating up the surface you're coating, you can decide if the atoms line up in a perfect, orderly crystal or if they just land in a more random, jumbled structure. Or look at sputtering power. You crank that up and the material builds up faster. It's this incredibly delicate dance to get the exact properties you're looking for. Which, of course, brings us to a huge question. When you've just made something that you measure in atoms, how in the world do you check your work? It's not like you can just hold it up to the light. You need a pretty serious toolkit. And here it is. This is the toolkit. To actually see the surface, scientists use things like a scanning electron microscope, or SEM, for these amazing high-res images. To check the internal atomic structure, they use X-ray diffraction, or XRD, to see if everything's lined up. To make sure the chemistry is right, they use another tool, XPS. And finally, to test its strength, they can use something called a nanoindenter, which physically pokes the film to see how hard it is. Now, for a long time, all that testing happened after the process was done. You'd make the film, take it out, and then test it. But the future, which is really happening right now, is building those measurement tools right into the sputtering system for real-time feedback. And that changes everything. Instead of just hoping your recipe turned out right, you are watching and adjusting it live, as it happens. This gives you unbelievable stability and means you can make the exact same perfect film over and over again. It basically lets scientists go from being molecular bakers to being true molecular architects, designing materials with a level of precision we've just never had before. And that kind of leaves us with this huge, exciting question, right? When you have this much control, down to the individual atom, what kind of impossible materials are we going to build next? Self-healing coatings? Super efficient solar cells? Things we can't even imagine yet? The toolkit is there. The only limit, really, is our imagination. Thanks for tuning in.